Hi everyone, welcome to the third lecture of this module on displacement sensors and accelerometers. Till now, we have covered various contact and non-contact displacement sensors, including potentiometric kind of sensors, eddy current sensors, then some capacitive sensors. We have also discussed about Hall effect kind of sensors, magnetoresistive devices. We have seen quite a lot kind of displacement sensors. However, we have seen that all of them has certain limitations, okay, and because of that another kind of devices is always required, particularly for specific kind of application. Okay, for non-contact application we have seen that this magnetoresistive kind of devices or Hall effect devices are very popular, all right, but there is another kind of device which is also very popular, particularly for displacement measurement, and they are categorized under optical displacement sensors. So what we will do today is we'll talk about optical displacement sensors, and then we will proceed towards discussion on accelerometers, which is a new kind of device that we are going to introduce in this module, and we will take up our next lectures based on accelerometers. Okay. So, as the name suggests, you have already seen a lot of optical displacement sensors in our previous modules. Okay. So, optical position sensor or a optical displacement sensor usually require at least three essential components, very similar to other optical sensors. You should have a light source. It can be a monochromatic source or it can be a broadband source also, depending on what kind of device or what kind of technique we are utilizing for this displacement measurement. Okay. So, you should have a light source, a detector usually in the form of photodetectors, and a light guiding device which can include some mirrors, some lenses, or if it is fiber based it should have a optical fiber and that kind of, or if it can be waveguides also. Okay. So, depending on what kind of technique you are using, you have all these components, all these three components present in your optical displacement sensor. Okay. Categorically we have various kind of optical displacement sensors, including some triangulation sensors, which is also known as laser displacement sensors. We have confocal displacement sensors, time of flight displacement sensor, laser Doppler vibrometers, which is also a kind of displacement sensor, but basically it is mostly utilized for vibration measurement. And then we have a very prominent interferometer metric sensors. There are other kind of sensors also based on grating and other things. We'll talk about them in brief. Okay. If I talk about a triangulation sensor or a laser displacement sensor, this works by projecting a laser beam onto an object and detect the reflected light with some specific sensor like CMOS sensor at particular angle. Okay. So, the angle of the reflected light combined with the geometry of the sensor, it gives you measurement of the distance or the displacement if you know the direction of the reflection. Okay. Then the confocal displacement sensors are also a kind of non-contact optical sensor, and they utilize chromatic confocal technology to measure displacement. Okay. Time of flight displacement sensors measure the displacement of emitting a light pulse and calculating the time it takes for the reflected light to return to its original position. Okay. That is how time of flight kind of optical displacement sensor works. Okay. Then we have laser Doppler vibrometers, which utilizes the Doppler effect, which we have already covered in detail, to measure the displacement in non-contact mode. Okay. Then we have interferometric sensor. These devices measure changes in the distance by analyzing interference pattern of the light waves. Okay. The very popular interferometric device is a Fabry-Perot based displacement sensor. So, to measure this small displacement with high precision in harsh ambient, this kind of devices can be applicable. Okay. So, a Fabry-Perot optical cavity is the backbone of a Fabry-Perot displacement sensor, and a typical Fabry-Perot chamber or a cavity looks something like this. Okay. So, this cavity consists of two partially reflective mirrors which faces each other, okay, and these mirrors are separated by a length L. Okay. Now, light from a known source, for example, it can be a monochromatic laser, is directed into the cavity, and inside this cavity the photons reflect repeatedly between the two partially reflected mirrors. Okay. And when they are reflected in between these two mirrors, they have interferences between them, or they interference each other. Okay. At certain frequencies, light can exit from the Fabry-Perret cavity. Of course, 99% will be reflecting, and say 1% or less than 1% is coming out of this Fabry-Perret cavity. Okay. Now, if you see, the interferometer is actually functioning like a frequency filter, okay, because the light is coming out at particular frequency. Okay. Now, its transmission frequency is closely linked to the cavity's length, and from the cavity's length I mean this distance L. Okay. So, this is the length of the cavity, and what I am telling you that the transmission frequency is linked to this length. Okay. So, as the cavity length changes, this length can be changed by, say, if this mirror is moving, or you say if this is stationary or this is moving. Okay. It can be attached to some object, for example, which is under movement. Okay. And accordingly, this plate can move from, say, this direction to this direction. Okay. So if this is changing, so if it is coming, say this plate has moved or this mirror has moved to this position, and say this distance is delta L. So now the length, the cavity length is L plus delta L. It can also be, say, L minus delta L if this this mirror will move in this direction. So this is now smaller by delta L. So now the new length is L minus delta L, right. So the frequencies at which it transmits light changes accordingly, okay, when the length changes. Okay. So if one of the mirror is made movable and other is kept constant, it becomes possible to detect very small changes in the cavity length. Okay. And this change I am talking about is of the order of some few microns. Okay. And this is done by monitoring shifts in the optical transmission frequency, something like this. So earlier it was here and it has shifted to this place. Okay. So the narrow bands of the transmitted light are spaced at frequency intervals that are actually inversely proportional to length of the cavity. So this del nu is equal to C by 2L, where C is the photon's speed and L is the cavity length. All right. So in practical applications, these cavities are of the order of, or of the length is of the order of, say, 1 mm, and if you calculate by this equation, the frequency will come out to be around 500 megahertz to few gigahertz. Okay. And that is how Fabry-Perret displacement sensor actually works. Okay. So by measuring the frequency shift of the transmitted light relative to the reference source, changes in the cavity dimensions can be detected with accuracy comparable to the wavelength of the light. Okay. So if you are using, say, 400 nanometer wavelength of light, the laser is transmitting, say, 400 nanometer, or say it is emitting, say, 900 nanometer of light, means that the accuracy that you are going to achieve is of that particular order. Okay. So any factor that alters the cavity length, okay, this can lead to the mirror movement, okay, can be measured, and this displacement can be because of applied strain, can be because of applied force, pressure, or it can be simply thermal expansion. Okay. Because of any kind of physical parameter, if there is a slight displacement or there is a slight change in the position of this mirror, okay, we will be able to detect if that change is of the order of the wavelength of the light that we are using as a source. So these devices are very, very accurate. Okay. However, this require very sophisticated tools Okay. However, there are very simple optical devices also available for crude displacement measures. For example, you can design a optical displacement sensor simply based on gratings. Okay. So an optical displacement transducer can be constructed using two overlapped gratings. Okay. These overlapping gratings act as a modulator for light. Okay. So the incoming pilot beam, just have a look on this diagram. So this is stationary grating, and there is one moving grating. So this gray one is the stationary grating, and this the black one is the movable grating. The incoming pilot beam, I have a cheap source of light, for example, first strikes the stationary grating. The position are adjusted in such a way. Okay. This grating actually transmits approximately 50% of the light towards the second grating, which is a movable grating. Okay. Now, when the opaque region of the moving grating align exactly with the transparent region of the stationary grating, okay, something like this, the light is completely blocked. Okay. As a result, the intensity of the transmitted light beam can be modulated between 0% to 50% of the pilot beam. Okay, something like this. Okay, and by this you will be able to measure the displacement by calculating the grating pitch. Okay. So we have seen in very brief what is optical displacement sensors, and if you see the advantages associated with these devices are their high resolution and their high accuracy. Okay. It is also possible to measure the displacement in non-contact mode, which is the requirement for most of the practical cases. Okay. These devices can measure very small displacement. Particularly, we have seen that this kind of Fabry-Perot kind of interferometers, even if there is a small thermal expansion, it can also measure that. Okay, means that it can measure very small displacements with very high accuracy. Okay, the good thing about these devices are they are immune to the electromagnetic interferences, which is very important, particularly when we talk about measurement of displacement in the order of few microns. Okay. However, they also have certain limitations, particularly they are very sensitive to the reflectivity of the surface, the object under consideration or object under measurement. Okay. Their performance is affected by ambient light, particularly if the ambient light interfere with the light source, okay, which is used for the measurement. Okay. Then they are limited to optical line of sight, and the cost involved in this kind of devices is really huge, particularly because of the costly detectors, the source, as well as the lens and mirror systems which are used to focus these light beams or photon beams. Okay. So we have to judicially use what kind of displacement sensor is required for our application, our intended application. I hope that you have now you have developed a basic understanding of the displacement sensor and where it can be easily applied, and what kind of displacement sensor is required for your intended application. Okay. So the ultimate aim of this course is to literate you about these devices, and even if you are not in the development or in the fabrication of these devices, I think you will be able, even if you are the end user of these devices, I think you will be judicially able to choose what device is required for your application. Okay. So with this we have finished our discussion on displacement sensors. However, still we are left with one very important position, or this physical sensor related to this position, velocity and acceleration, which is accelerometers, which is nowadays integral part of any electronic system or electronic gadget. So let's talk about accelerometer in little detail. Okay. So it is very clear from Newton's law and other law of motions that position, velocity and accelerations are interrelated, right? So velocity is the first derivative of position with respect to time, while acceleration is the second derivative of the position. Okay, so all these are interrelated. So just differentiate the displacement equation, you will get the velocity, or you can get the displacement by integrating it with the required limits. Okay, you can also differentiate the velocity term to get the acceleration, while it can also be integrated to get the required physical quantity. Okay, however, in a noisy ambient, differentiating signals can lead to significant errors. You cannot have a differentiator everywhere placed because there will be certain errors which will be associated with the differentiator that you are, or integrator that you are putting. Okay, so when complex and sophisticated advanced signal conditioning circuits are mostly utilized for this kind of application. Okay, so velocity and accelerations are not derived from position detectors. However, there are specific sensors which we can develop to measure these quantities. Okay, the equation force equal to mass into acceleration is very important for our measurement. So we will be using this particularly if you talk about spring kind of arrangement. Say we know that this F, the force is also related to the position for a spring kind of device by the spring constant. Okay, so this force equal to kx and force equal to mass into acceleration, they are they can be equated to get the acceleration if the position is known, or this x can be calculated by having various different kind of device. It can be, say, capacitive, it can be based on optical devices, it can be based on magnetic devices, there are thermal devices also. Okay, and then for this kind of measurement, you have measurement of force by compression or bending. So you can have piezoelectric or piezoresistive devices. So if you see this scenario, I can have a number of accelerometers or acceleration sensors based on all these points. Okay, so we'll see that in next part of our lecture. However, what is important is I have mentioned in the previous class also that there are certain criteria which are very specific to accelerometers, so we have to understand them. Okay, so acceleration sensors can be analyzed based on a number of criteria. That criteria can be a simple operating range, it can be a frequency range, it can be a linearity of the device, the sensitivity along a axis as well as cross axis sensitivity. Okay, so let us see some of the parameters which are very crucial for the case of accelerometers. Okay, the first criteria we'll see is sensitivity, because this is important for any kind of accelerometer. Okay, so sensitivity of a accelerometer is defined as the ratio of an electrical output to mechanical input. So sensitivity is given as del E divided by del A into E naught, where E naught is the original value of the electrical signal without application of any external acceleration, while this del A is the change in the acceleration which should be the working range, and this del E is the change in the electrical signal, and this can be in the form of current or voltage or other electrical parameters. Okay, so depending on the sensing mechanism, the commonly used units for accelerometers sensitivity are like MV per G, kilo ohm per G, picofarad per G, etc. Depending on what you are measuring and what is the electrical parameter, it is voltage or it is resistance or it is charge. Okay, however, in this units, this G is the acceleration due to gravity. All right, so the sensitivity is generally measured at a single reference frequency of a sine wave kind of device, okay, sine wave kind of signal, okay. In some country it is 100 hertz, or in certain country it is 160 hertz, depending on from where you are buying these accelerometers, okay. So this frequency response of this device of an accelerometer looks typically like this. You have this x-axis in the form of frequency, and this is the natural frequency of this device, a typical accelerometer, and the reference frequency will be little lesser as compared to the natural frequency, okay. So the reference frequency, as I have mentioned, in most of the cases is around 100 hertz, okay. Then you have cross axis sensitivity. It is little bit different than the sensitivity that we have just seen. It measures output on one axis when acceleration is applied to another axis, okay. So if you see the definition, this cross axis sensitivity is defined as the sensitivity of plane perpendicular to the sensing direction in relation to the sensitivity in the primary sensing direction, okay. So mathematically, cross axis sensitivity is given as sensitivity of the axis perpendicular to the sensing axis divided by sensitivity of the main sensing axis, okay. They are denoted as SP and SS, and cross axis sensitivity is given as SC, and since it is represented in as a percent, okay, so this SC is given as SP by SS into 100%, where SP and SS, as I have mentioned, are sensitivity of the axis perpendicular to the sensing axis, and SS is the sensitivity of the main sensing axis, okay. Then frequency response, we have just seen. The frequency response describes the output signal of the sensor, the accelerometer, across a range of the operating frequencies, all right. Then there is another term which is very crucial for accelerometers, which is zero stimulus output. The zero stimulus output, particularly for devices like capacitive or piezoresistive sensor, is defined when the sensor's sensitivity, when the sensor's sensitive axis, the active axis, is perpendicular to the Earth's gravity, okay. So in sensor with the DC component in their output signal, the effect of gravity has to be eliminated before the output, as no mechanical input is determined. So when there is no input stimulus, then also this accelerometer, it's very common that it shows certain output, okay. So when there is no acceleration, ideally there should be zero output, but then there is a certain offset which is defined by this zero stimulus output, okay, which has to be assessed before the accelerometer is in deployment, or before it is deployed for the measurement, okay. One important thing I just want to talk before we actually move to the different type of accelerometer. The thing that I wanted to mention is the concept of proof mass, okay. So an accelerometer requires a special relative massive component. Any kind of accelerometer that we are going to see, any kind of, irrespective of what kind of device it is, the accelerometer requires a special relatively massive component whose movement lags behind that of accelerometer's housing, okay, which is coupled to the object which is under study, okay. So displacement transducer can be used to generate an electrical signal as function of the acceleration, okay, and this massive component is usually called either a seismic mass or inertial mass or a proof mass. So in this course we will be or in the next two lectures we will be mostly talking about this proof mass and how it accelerates with respect to the housing or the enclosure of these accelerometers, okay. So we will be using this word regularly. Seismic mass, inertial mass, proof mass, all are same, okay. So depending on what principle we utilize for this measurement, we can have a number of accelerometers. We can have capacitive accelerometers, piezoelectric and piezoresistive kind of accelerometers. We can also have thermal accelerometers, which are very important, particularly they are of two different types, and some of them are very important for certain kind of application we are going to see in our last lecture. Okay. And then we also have non-contact accelerometer like other devices, which is based on optical principle. So we have optical accelerometers, and based on magnetic field also we have one kind of accelerometer which is known as Hall effect kind of accelerometers. Okay. So what we will do is we will talk about these accelerometers one by one in our next class. We'll start with capacitive accelerometers, and we'll also try to see that how these devices can be fabricated in the clean room. Okay. So we'll talk about these accelerometers in more detail in our next class. Thank you.